Hi, I'm Heath Borders from Jive Software, and this is Modern iOS Apps with Swift. So, what I'm going to talk about today is Jive Swift history, sort of where we started in Swift, how we progressed through some of the risks that we took on going through various versions of Swift. And then we're going to get into a little bit of the microcosm in terms of how to interoperate between Objective-C and Swift, and then some patterns that have emerged that are fairly Swift-specific and that are pretty widely applicable and a little bit revolutionary compared to common things that you see within Objective-C. And then I'm going to walk through the architecture of Jive's JiveX Community Manager app and how we use that to greatly improve our team's performance, not just with the Swift language, but also just in terms of our engineering practices. So Jive's Swift project is our JiveX Community Manager app. So the way that what JiveX is a user forum generally for customer support. So a lot of Fortune 1000 uses this. And when users post things on user forums, occasionally they post things that are objectionable or that are spam, and you have a community manager whose job it is to receive these notifications and moderate them. So our app receives push notifications from the Jive server and then displays them. The user can moderate them, yes or no, and there's a few other integration points that allow the community manager to interact directly with the community on their mobile device. This uses JSON services, so as most of your apps probably do. We use core data for our local caching, which you might or might not use, but this is Apple's preferred way to do things. And in terms of functionality, just to give you an idea, this isn't just sort of a toy trivial app. I mean, we have an inbox that's kind of similar to like a Facebook timeline. We have the moderation queue that I mentioned. We have the ability to search content within the community. We have the ability to view individual user profiles within the community. And then we can also obviously view content within the community. This is 45,000 lines of Swift in production. And when we talked with Apple at DubDub 2015, apparently, according to the guys that we spoke with, we were one of the larger Swift apps that they had heard from at that talk or at that conference at the time. So that was almost 6 months ago. So things may very well have changed drastically. But among the people that I talked to, we are still one of the bigger Swift apps. And then this is also 17,000 lines of Swift test code. And both of those, by the way, were just determined by that bash line below. So, you can take that with a little bit of a grain of salt. So, switch. Go on. There we go. So we started with Swift 1.1 in December 2014. The reason we actually ended up doing a complete Swift rewrite is because our Objective-C code base was just kind of a mess. We were sort of forced into a lot of technical debt by demanding customers that had a lot of money, which I'm sure nobody here has ever experienced before. And so as a result, then, we ended up deciding, no, we're just going to completely start over from scratch and really do things right this time. And I think actually we did stick to that. I didn't actually want to even begin in Swift because of all this risk of tooling. But my manager was certain, no, Swift is the way of future, so we went ahead with Swift. So I got started with Swift 1.1 in December 2014. I had about a month ahead of the other team because I rolled off early, and they sort of shut down the original project and put it into maintenance mode while I went ahead and tried to get a hold of architectural best practices, language best practices, CI best practices. We converted to Swift 1.2 after Xcode 6.3 went to Gold Master. We converted to Swift 2 after Xcode 7 went to Gold Master, but we did not adopt the Swift 2 beta when that was available, I think right after DubDub. So there was about a 3-month period where Swift 2 was out, but we were not using it at all because we needed to be able to release our code in the meantime. And this is a problem you're going to encounter with Swift, is that it is not backwards compatible and is not forwards compatible. You're generally speaking only going to be able to build Swift for the Xcode version that you're currently working with. So if you have delivery deadlines, you need to stick with the Swift version that you can currently deploy to the App Store, which in our case was Swift 1.2 until I think it was late August, early September when they finally released Xcode 7. And then it took us about a month to do the conversion between, it was actually me doing the conversion from Swift 1.2 to Swift 2. And a lot of that conversion issues, a lot of those conversion issues were simply a bad decision I made early on. So Apple has changed the Swift syntax and Swift language rules a few times, and I don't think they're going to make as many drastic changes in the future. But one thing that we ran into was, if you notice up there, we have the func foo and func foo hash bar. So that was, the idea there was that when you call the foo function, you need to supply the bar argument name. Apple's official recommendation was the second one, to say foo with bar, which you're probably familiar with from Objective-C. And that ended up being very important, because then in Swift 2, they made the first declaration illegal, and if you wanted to force someone to use an argument name with the first parameter, you had to declare it like the third function, which is foo bar bar bar, which is just ridiculous to write, and we were not going to do that. So if you use the auto conversion tool, we were going to end up with all these foo bar bar bars everywhere, and that was completely terrible. So we decided instead to migrate all of our stuff, and it just took a long time to go through and touch literally all of the 45,000 lines of code. And then we actually converted to Swift 2.1 immediately. We didn't actually even finish the Swift 2.0 conversion. Then Swift 2.1 came out like a month later, and we went right into that. So now, going between Objective-C and Swift. Great news, if you have a giant Objective-C code base and you want to migrate slowly to Swift, you can do that. You can call all of Objective-C from Swift really easily, and then if you adopt, as you can see in the methods there, foo with bar in Objective-C turns into foo with bar as an implicitly unwrapped optional. That's what the bang after bar means. If you use the modern Objective-C nullability annotations, you can even get rid of that implicitly unwrapped optional and explicitly declare it as nullable or non-nil, and that'll make it look like a nice proper Swift function. However, the real downside is that if you want to write a reusable component that your Objective-C needs to be able to call, you are very, very restricted. There's a very limited subset of Swift that you can use from Objective-C, and you cannot subclass Swift classes from Objective-C at all. So you shouldn't be using subclassing as your means of extension. You should be using composability dependency injection. However, on the Swift side, that's not why they force you to do this. There's runtime limitations. But as a result, you just full-on can't subclass. So if that's central to your design, it's going to work out badly for you. There's more than it, and you can do even less than simply not using structs or not using optional scalars. But those are the two that I ran into that hit me the worst. I had to convert a lot of struct code to be classes in order to make our code interoperable with Objective-C. Now, and when I get into the microcosm and how to handle individual, or how to adopt individual patterns, I want to talk a little bit about pain. Specifically, I think it's important that when you're trying to teach people new things, when you're trying to present new solutions to people, they need to see the need for it. They need to feel the pain associated that your solutions are curing. And so without that, it just seems like you're this autocrat, handing stone tablets from above. You need to allow them to try to come to these terms on their own, ideally, but if not, at least have a way that they can provide their own solutions once you give them these tools. And the real quote here, the quote, "For students to learn what we intend to teach them, they must have an intellectual need for it." That's from a elementary math education paper, but it really instructs well the proper way to kind of adopt these very, very revolutionary patterns. So one of them is really simple. This is use results instead of errors. So this is very common Objective-C code that you've probably seen all over the place. This is the Cocoa error handling paradigm. And the downside of this, one of the pains that probably nobody dealt with before Swift came along, is that you have invalid state. So there are actually 4 tuples that can be returned from this method. You could have a non-nil foo and an NS error. That's valid. You could have a foo and a nil NS error, which is also valid. So you either have success or failure. That's what we expect. But there's actually 2 more that the type system allows. Foo and the error could both be nil, And most of the time, nobody cares about that because we go ahead and figure, well, we'll just show that as a nil error and nothing really bad happened. But really, that's a pretty fundamental flaw in our type system, and a fundamental flaw somewhere somebody screwed up. Also, you could have a non-nil foo and a non-nil error, and usually that's treated as a success. And in fact, actually, the Cocoa design docs specifically say that you should treat that as a success. However, somebody probably screwed up there too. You generally shouldn't have that happen either. So the solution is the result type. The result type uses Swift enums, which in the sort of programming language theory camp, they call this a union type. And you're unifying the success case, which is the value that could be returned, and the failure case, which is the error that can be returned. So every time you have a result, you have to explicitly say that you don't know which of those two things it could be, and then you have to explicitly unpack the result and get the value out or get the error out. And that forces you to confront your error up front immediately. But then we run into some pain from composition. So this is just some familiar Objective-C code. Again, if you need to compose these two things together, you're going to first call create bar fail with error, and then you have to check the bar, and then you're going to pass that to create foo with error, and then you're going to check the foo. And then you've got two different failure cases that you have to handle that are often going to be the same, because usually you're just going to log it or show it as an error to the user or something else. Most of the time, these are not recoverable errors. And you don't really get much benefit from Swift here either. This is how you'd unpack the result, and this is how you would check for the errors. And so as you can see, we have to use switch to unpack the union type, and not too great either. But this is an important part that I think you are still solving the pain of invalid tuples. So allow your teams to write code like this and to feel this pain of multiple error handlers and nested switch statements and kind of a little bit complicated code. You don't need to acquire too much technical debt, but allow them enough that they kind of say there's got to be a better way. And then hopefully they come along to it, or you give it to them. You give them map. And so map allows you to solve a little bit of the pain problem, because if you need to take the result of an operation and transform it into something else that itself can't fail, it's pretty easy to do that. So as you can see, we have create bar here, and that returns a bar. And if you want to adapt that into a BAS, it's very easy to change that into a BAS result with map. However, we have a new pain, and that is if you need to call create foo with bar, you end up with a nested result. You have a result within a result. And if you need to do this over and over again, your result just gets bigger and bigger and bigger, and it's really untenable and impossible to manage. And again, allow your team to feel this pain, because then you can present them with another solution, which is flatMap. And flatMap is a means of collapsing these nested results together into a single coherent result that's what you expect. So from the original createBar.map, we can call instead createBar.flatMap, which knows to utilize either the result from create foo with bar or return the error from create bar if bar failed. So as I said, let the team feel the pain. Start with result, because just like my team, most of the other teams I've talked to, you're probably just ignoring those other two invalid tuple cases anyway. So start there as an initial point. Let the team feel the composability pain. Let them feel the result within the result pain, and then present them with your solutions. Now, unfortunately, there is some ongoing pain that you're going to have. Swift has the optional type that is kind of like a result, except you either have some value or none. However, you don't have an actual error associated with it. And generally speaking, your result types are going to attach an error to that none case. So if you try to create a URL from some input, and NSURL will return none if it was not a valid URL, you might want to attach an error to that and say, hey user, you screwed up. You need to enter some valid URL text. It's not trivial to make these optional types interface directly with an arbitrary result class because of some limitations with Swift's type system and with exports to optional. However, this has improved a lot with Swift 2 with protocol extensions and type constraints, and I just haven't gotten a chance to work on adapting that because of how long it took us to convert from Swift 1.2 to Swift 2. So just something to keep in mind. Then we have this notion of futures instead of callbacks. So this is some probably pretty common Objective-C code that you've seen, where you call some asynchronous method and then you issue a block callback, or you call a block callback. And as you can see, we have the same sort of invalid tuple situation. So we know up front that we should probably be returning results instead of these errors and literals. And then if you end up with a situation where you depend on multiple different types, or multiple different calls, you end up with this same situation. Looks very similar to our result classes, where you fetch your bar, and then you have to check the bar result, and then you have to fetch foo, and you check the foo result. And if you notice, I didn't even include the error cases because I wanted all the code to fit on one slide. And this is, again, how easy it is to skip over the errors. So again, we have our solution. We can solve this with map, and we can actually go and grab the bar. We can issue our call to fetch bar, and if we again want to convert that to a BAS, it's very easy because there's no failure case. So we just take the bar and we call BAS against it, and you've just transformed your bar future into a BAS future, and that's great. But if you need to call another future inside, if you have to fetch a foo with your bar, then you end up with this double future problem, just like we had the double result problem, where you have your fetch foo with bar, which in turn, if you just use map, will return a future within a future. And so again, the solution there is flatMap. So we can, instead of using map, we call fetch bar flatMap, and flatMap knows to use fetch foo with bars to return fetch foo with bars future if fetch bar succeeded, and to return bar's error if fetch bar failed. And so with our ongoing pain there, just like you had issues interfacing with optional with result, you're going to have some issues interfacing with optional with future. You'll also need to maintain probably parallel APIs between future and result. Because these transforms deal either with results or with futures, you can't use the exact same APIs with a protocol. So you just have to, you as the API author, have to maintain these parallel APIs yourself. It's not that big of a deal, and it's mostly for the good of your consumers. We also don't escape asynchronicity. You still have issues where if you have two parallel futures going at once, then you need to ensure that you handle out-of-order execution and various other things. That still exists in Objective-C as well. We haven't made anything worse. It's just an essential complexity of the system. But you may have noticed some similarities between result and future in that they both had map, they both had flat map, and in fact, as an exercise to the reader, I encourage you to look at Swift's array and optional classes, which also have map and flat map. And if you really want to get adventurous, after your team has invested time in learning about results and learning about futures, then you can go forth and adopt Reactive Cocoa, which is written by some people that are much smarter than me, that have thought much more deeply about this problem and have really provided a really good solution to the general case. I still think that it's important to take these incremental steps because it allows your team to really internalize the reasons behind these changes and paves the way to using Reactive Cocoa. And so now that we've gotten through the microcosm, I'm going to walk you through the architecture of the JiveX community app. And so we broke this up into a series of independent modules or I should say, of this dependent module graph, and some of which could be independent. Each blue rectangle there is itself a module, and then the arrows represent dependencies. So data depends on entity, view depends on entity, etc. So we'll start with sync. And our sync module provides a server-side API for the client. So this is basically Jive exports a standard core JSON API over HTTP. This is basically what a lot of people are going to be using. We actually used AlamoFire for this, which is the successor to AF networking in Swift. It wraps NSURL sessions, so we don't have to deal with NSURL session directly. And there's nothing wrong with dealing with NSURL session directly But by using Alamofire, we get a community of people that are all solving the same problem, all have to work within NSURL session. So even though we are very accomplished at dealing with Cocoa networking APIs, it's very good to have this focused community. We haven't really found too much value in trying to work with people over the Apple Dev forums, but we found a lot of good success working with teams that are dealing with Alamofire. And then also for our JSON mapping, we are using Object Mapper. Object Mapper is a terrific framework for handling the actual, not parsing of JSON, but transforming of JSON object structures into arbitrary data transfer objects. The most Swift libraries that you see are just dealing with JSON parsing, and then they emit a bunch of dictionaries and arrays and scalars for the Swift structure. This actually takes it a step further and maps your JSON structures directly into one of your business objects. Our sync module is stateless, and this is important. So although we do have a little bit of state for our cookies for our HTTP connections, each individual HTTP transaction is completely independent, and as a result, each sync transaction is independent. Sync just deals with making the HTTP transaction or HTTP call and parsing the JSON into Swift objects. And we test all of our public methods within sync just as part of the sync module with our real Jive server. If you have a server that's either really simple or you feel really confident that you can mock it without losing any behavior across new releases of your server, then you might do that as well. A downside to our approach with a real server is that we were not able to create certain error cases because, like network failures or other things that just weren't really possible to emulate without mocking. So then we have our entity component. This contains no logic. These are just DTOs that handle the dependency between data and views. So this represents a single unified data object that we use throughout the rest of the application that is part of our working set. In our case, we are using core data, so this is we accomplish this with an XC data model. Additionally, you should have your interfaces for events. If you're using something other than core data, then you need to make sure that whatever events that your data layer produces needs to be available in entities so that your views can consume them. In our case, we were using NSFetchResultsController, so we were able to export NSFetchResultsController as our eventing system, and thus the view could see it because it was standard foundation. Because there's no logic here, we didn't test anything. You could, in some extreme cases, I think you could write tests to ensure that you have the proper types associated with your attributes and to ensure that you have that you can perform saves with optional attributes. But I don't think that there's a lot of value to be added by writing tests that exactly describe the specification you've outlined in your XC data model. So we didn't do that. Then we have our data layer. This contains our create, update, fetch, delete logic. This also is where we create our event sources. So in our case, our event sources were NSFetchResultsController, and we export this up through our hierarchy so that the view can consume them and directly receive data events as our data changes. All of our state resides in the underlying data source. We don't have any. Again, all of our data transactions are independent. We don't have any state lying in the actual data objects themselves. It all falls into the core data persistence store. And we tested all of our public methods. This is a great place to incorporate property-based testing because you have so much interdependence. Generally speaking, your underlying persistence store has so much interdependent state, it's very difficult to test all of the different state relationships that exist. So now we have our service, and the service ties sync and data together. So this provides business transactions, and again, these are ideally independent business transactions. There's no state in service except for in the underlying data layer. Most of what service does is translate our sync objects back into data objects. So when a sync call returns, it returns JSON objects, and then data does not have any dependency on sync, so data doesn't understand how to consume those sync objects and put them in the database. That's what service's job is. And then it also forwards through the NSFetchResultsController, it forwards the data events upwards through higher up in the architecture. And finally, we test all of our business transactions, again, with a real server using the same server we use with Sync. And model is where stuff really starts to get interesting. So model is the place that holds all of our user state, all ties really all the functionality of the app together. This is a place where you could theoretically use all of the app in a headless mode. You can write complete end-to-end tests here, and you can verify that any state you should be able to create any state your app can get into only within the model. You can test as much of that as is feasible. In our case, we just tested the happy paths and then really obvious expected error cases like the user failed to log in, something like that. The view we have both UIViews and UIVieWcontrollers in our view. The reason for this is because views and view controllers together, I believe, represent view logic. Even though Apple wants, in all of Apple's examples, they tend to put a lot of business logic inside the view controller, and they tend to think that the view controller should be the root of your app's architecture. You also have a lot of view logic imbued within the view controller. You have UI fetch control that can only, UI refresh control that can only exist on a UI table view controller. You have UI view transitions. You have UI navigation controller that handles which views are currently visible to the user. So we wanted to keep all that logic completely isolated because in our old application we had way too much business logic getting mixed up with our view logic, and in some cases we even had direct core data calls directly inside of a view subclass, and it's just far too easy to mess that up. So then also the view consumes our entity results and events directly via the NSFetchResults controller. You don't have to use NSFetchResults controller. You can emit events using whatever system you want, but NSFetchResults controller ties in pretty nicely with UI table view. So that was why we did that. We have delegates on the UI view for all the UI control callbacks. So that means that when a UI control emits an action, the view captures it and then reissues that through a delegate method. So for any given view controller within our system, we have a delegate that corresponds to all of the interactions that the user might do, that the user pulled to refresh the inbox, that the user tapped a button, etc. And because we're using we don't have any dependencies on our real data, we can use fake data and create snapshot tests with this fake data. Our UIs were changing so frequently that we didn't feel it was prudent to do that. It would just require too much constantly updating the app. And finally, at the top of the architecture, we have our presenter. This ties the view delegate into model calls, and it also translates model events into view updates. And it's stateless. It also translates our iOS UI application events into model calls. So these events are things like application did enter foreground, application did enter background, if you receive a push notification. Those things all are coming off of the UI application. And ideally, the UI application would be sort of part of the view logic as well. However, we really felt like the presenter is a good place to have all of our dependencies because all of our dependencies live together within the presenter. It makes a lot of sense to have that be the place that you build the actual app that you're going to deploy in the App Store. So that was a slight compromise we made. So that's our architecture in place, and now I'm going to walk you through an actual interaction with our system. And I'm going to make these slides available afterwards, so you don't need to feel like you need to write all this down. So with our inbox, this is a screenshot of our inbox, and on the left you can see the different cells that are available for different inbox items in the timeline. So if the user pulls to refresh the inbox, that means they want to check to see if they've got any new data. So that purple arrow the first purple arrow going into the view box represents the pull to refresh event. So the UI view receives the pull to refresh event callback from the action. I think it's the the value changed event callback, and that view then emits a delegate event to its presenter. The presenter then issues a method call from that delegate event into the model to say, okay, the user wants to refresh the inbox. So this is where our actual user logic and our actual business logic gets kicked off. The model then immediately issues an event back up to the presenter to say, okay, our state has changed. We are now refreshing the inbox. And that in turn causes the presenter to tell the view, put your view in inbox refreshing mode, and that's what you see there on the right, where the refresh control is now visible. Similarly then, while after the model says we are in, or after the model emits the event to say we're in refreshing mode, it's also going to begin the transaction to refresh the inbox. And it does that by telling the service, give me an inbox refresh transaction. The service in turn calls sync and says, make an inbox refresh sync call, which in turn calls the HTTP method. Then the sync method returns, and it parses our JSON and returns that to the service, which in turn unpacks the JSON objects and sends them to our data module. The data module then asynchronously processes that and will emit events in the next slide. The service also returns to the model and says, "Hey, our inbox refresh operation is complete." The model then emits an event saying, "Hey, we are not refreshing the inbox anymore," and the presenter captures that event and translates it into a method call to turn off the UI refresh control in the view. And so that's what you see to the right. So now the view has returned to its original state before the user refreshed. And then finally, the data module has completed its processing, and it emits an event directly to the view. Even now, again, if you remember in the architecture, data and view didn't have direct dependencies on each other, but because we were sharing the NSFetch results controller, the service and the model and the presenter can pass that exact object all the way over to the view, where the view can attach a listener and handle these events. And then that's, as you can see on the right there, I have a new inbox item. And even though it might look kind of clunky when I play out the individual pieces, all this processing is so fast that it looks seamless to the user. So then, just to talk a little bit about some of the constraints and effects that we had within the system because of Swift. So because of Swift, all of your modules need to be frameworks. You can't do any static libraries within your system. This can be a problem if you've previously used static library modularity, which you could not have possibly done before iOS 8 because you could not use frameworks before iOS 8, which is another problem with Swift. If you want to use any kind of modularity, you need to be targeting iOS 8. You can use Swift with iOS 7 if you want to, but you then have to put all your code into one project. It's not possible to use any kind of static compilation. Also, separate frameworks compile faster, which is nice. Let me bring up our architecture slide again. If you have to recompile something within Entity, then you have to recompile all of the dependencies of Entity, so basically the entire graph. However, if you only have to recompile something in View, then you don't need to recompile model, service, data, and sync. You only have to recompile View and presenter. And this really adds up quickly. Our entire app, if you do a clean, so you have nothing compiled, and build and run, took 1 minute 30 seconds on my 2012 MacBook Pro. If I just recompile a single class in presenter, I can rebuild on the simulator in 5 seconds. In some cases, I know some people that are building a Swift app that has to run on iOS 7. It takes them 5 minutes to compile every single time, no matter how big or small their change is, because they have to recompile their entire code base every single time. This has actually improved quite a bit over Swift 1.1 and 1.2, which I believe they had said their whole application was taking up to 10 minutes to recompile. So I really don't even know how these people actually did day-to-day work this way, but that was their choice. And then to talk a little bit about our build pipeline. So as I mentioned, we have these separate modules. Every module has its own separate workspace, and that way each one of these modules can be built independently. So we actually have way more modules than just these. These are just the major ones, but everything has its own independent build. So if somebody breaks something, it's very easy to pinpoint exactly where the break occurred. These isolated workspaces guarantee modularity. So as I mentioned before, it's not possible for you to put networking code in your views because your view can't even see the sync module. And it's not possible to, it is unfortunately possible to put all of your code inside the presenter module. So it's very important to do really tight code reviews on that module. However, because the presenter module only maps model events into the view and view events into the model, it should be really thin. So there really shouldn't be anywhere for bad code to hide there. The great thing is, let me go back to my architecture slide real fast. Because of this architecture, we have some really nice engineering task parallelism available. So when we are building the inbox, component, we have 3 different pieces that can be independently worked on. Once we've identified what our entities are going to be, separate engineers can work on the view, the data, and the sync components, and those are the 3 things that take the longest to do. In the past, we had one engineer would do the entire thing himself, him or herself, and they'd walk through the entire application, and then we'd have a knowledge silo on how the inbox worked. And it would also take longer because they would have to, in series, write the sync piece, and then write the data piece, and then write the view piece. Now we can take 3 people, throw them all at the project. We can give everybody a little bit of domain knowledge on what the inbox means, and and avoid problems if somebody gets hit by a bus. Similarly, if somebody wants to specialize and they just want to be the view guy forever, or we wouldn't let them do that forever, but they want to do it for a while and they really want to dig deep on what UIKit means, they can work on the inbox view, they can work on the search view, they can work on the content view. And so it gives us a lot more flexibility versus in the past on our old app, we had one guy that was the inbox guy, that was me, and we had one guy that was the content guy, that was somebody else, and we only talked to each other at our few integration points. So it made us a lot less flexible. And that's it. Any questions? I think Mike is going to pass the mic around. He's got a mic. All right. There's one over there. And oh yeah, you have a mic, so I don't have to repeat. That's nice.
Just a quick question about Swift. So you're saying that Apple makes frequent changes to the grammar, the language itself, and will basically say all of this code you got to redo it because
no, you don't. So you don't have to redo it all. Let me walk back to that slide and I'll talk about the individual changes that we had to deal with between each version. There we go. So from Swift 1.1 to 1.2, they changed their casting rules. So it used to be that you would say if you want to cast a string to an NS string, you would do just the word as. With Swift 1.2, they forced you to change that to an as bang. So that wasn't that bad. I think we only had like 3 places where we did that. But Swift 1.2 to 2.0, yes, they got rid of that pound sign to denote a required parameter name. That bit us really hard. Now, at the time when Swift was still really in its infancy in 1.1, there was a lot of debate back and forth as to what was really proper naming style. And I really liked having a uniform style where every parameter has a name. And also it was less typing. So as you can see up there, foo pound bar or foo hash bar is a lot less than foo with bar or foo bar, or foo bar bar. So it was a lot nicer in a lot of ways, but it was kind of a gamble and it didn't pay off. So I think largely as long as you are following Apple's guidelines for how to name things, they aren't out there to try to screw us over. But the downside is that there are cases where, as the change from Swift 1.1 to 1.2 signifies, it was not possible to take Swift 1.2 code and compile it with a Swift 1.1 compiler or vice versa. So if we ever had to use, like git bisect, for example, to walk back through, one of our git bisect steps would have to include installing Xcode 6.2 instead of 6.3. So this is something that you need to be aware of, is that bit rot is a very real thing for Swift. And I think for 2.0 to 2.1, we didn't have any changes that impacted us there. There are some more advanced things, mostly having to do with protocol type constraints, protocol extension type constraints. But since we weren't using those yet, it hasn't bitten us yet. But it will. Like if we try to walk back, we're just going to be screwed. So anybody.
The architecture model is pretty clear. My question is, so are all your presenters in the same workspace then? So an inbox, and do you
Yes.
see that as your app grows in complexity that will also be separated?
We have been discussing that, whether we want to, there have been a couple of angles there actually, whether we want to separate all of our presenters into individual workspaces and have kind of an inbox workspace and a moderation workspace and a search workspace. I don't think we're going to be there yet because our presenters really are very, very thin. But the flip side is that if we want to reuse these outside of other projects that are completely separate, then that might be something that we want to do to allow other teams to consume our stuff. And I think that's my time. So I'm available, around. Grab me, and you can even see some of my source if you want. I won't give it away, but that's it. Thank you.